Okay, welcome back to COIC 2325. This is Chapter 1, Part 2. We left off at data representation, so we're going to start talking about data representation and finish with Boolean operations. So in data representation, we're going to look at binary numbers. How do we translate between binary and decimal numbers? And if you don't know what binary and decimal numbers is, we'll look at that. We'll do some binary addition. Integer, we'll talk about the integer storage sizes. Hexadecimal integers, translating between decimal and hexadecimal. Hexadecimal subtraction. We'll look at signed integers, and then do some binary subtraction and character storage. So let's start with binary numbers. So this here is a binary number. So binary numbers are represented using ones and zeros. 1 equals true, 0 equals false. So looking at this binary number, we are going to always talk about the least significant bit and the most significant bit. So the least significant bit will always be at the end or the right hand side. We'll also look at how we number the bits. So when we are numbering the bits, we don't start with 1, we start with 0. So this is 0, 1, 2, 3, 4, 5, 6, all the way to 15. So there's 16 bits here in this particular binary number. And again, each digit or bit is either a 1 or a 0. Each bit represents a power of 2. So each binary number is a sum of powers of 2. So if we look at this position here, so this is position 0, this would be 2 to the power of 0. 2 to the power of 0 is going to have a decimal value of 1. Decimal values are the numbers that we use in our system, the decimal system. So just like you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, those are decimal numbers, and that's the decimal system that we use. And so the next position, so position 1 is 2 to the power of 1. 2 to the power of 1 has a value of 2. So the decimal value for this here, for this position, is a 2. And the decimal value for this one is a 4. And 2 to the power of 3, 2 times 2 is 4. 4 times 2 is 8. So this 2 to the third power, this value of this binary number is an 8 in decimal value. So if we look at, okay, let's go to this slide. If we look at how do we translate a binary number to decimal, then all we're going to do is we're going to look at each bit. We're going to convert each bit to a decimal number, and then we're going to add those decimal numbers. So here's an example. We have 0, 0, 0, 0. That's 4 bits. 1, 0, 0, 1. So this is 8 bits, and 8 bits equals 1 byte. And it represents, this binary number represents the decimal 9. So how is that calculated? So we just look at the positions in the binary number that have a 1, and we ignore all the ones that have a 0. Because the way that we calculate it is that we say binary digit, the binary digit times 2 to the power of the position of that digit. So 0 times whatever is going to be 0, so there's no need to calculate that. So we're just going to calculate the ones that have ones. So this position we said was 2 to the power of 0, right? Because this is position 0. So 2 to the power of 0 is 1. 1 times 1 is just 1. So this here is worth 1. 2 to the power of 3, 2 times 2 is 4, 4 times 2 is 8, 8 times 1 is 8. This is worth 8. 8 plus 1 equals 9. So binary number 0000101 is a 9 in a decimal number. So now I want you to try it out. You can pause this video and go ahead and see if you can figure out what is binary number 0001101. So again, we ignored all the zeros. We are going to start with this one right here. So this one is at position what? 0, 1, 2, 3. So this is position 3. So we multiply 1 times 2 to the power of 3 and we get 8. This is position 2, position 0, 1, 2. 1 times 2 to the power of 2. 2 squared is 4. This is 2 cubed, 2 squared, 2 to the power of 0 is 1. 8 plus 4 plus 1 is 13. And this is the decimal value that's equivalent to this binary number. Okay? And this is what the machine understands. A machine only understands ones and zeros. Okay, so here we're flipping it around. How do we convert a decimal number into a binary number? So if we have the decimal 37, you take your decimal number and you divide that decimal number by 2, and then whatever remainder you have, that's going to be the digit of the first digit of your decimal number. And notice here that we're going to start with the least significant digit. So we're calculating the least significant digit first, okay? So when we divide 37 by 2, we get 18. 18 plus 18 is 36, remainder of 1, okay? So there's a 1 right there. Then you take that 18 and divide it by 2 and you get 9, and there's no remainder. 9 divided by 2 is 4 with a remainder of 1, because 4 times 2 is 8. You have a remainder of 1. 4 divided by 2 is 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. 1 divided by 2 is going to be 0. 0 with a remainder of 1. So 1 divided by 2 is 0 with a remainder of 1. And so the binary number for the decimal number 37 is 100101. You have 1, 2, 3, 4, 5, 6. So you would just add, to make it a byte, you would just add 2 zeros, 7, 8, 2 zeros right there. Okay, so go ahead and pause the video and see if you can figure out, before we go into binary addition, see if you can calculate the binary number of the decimal number 25. So decimal number is 25. So how do we calculate the binary number of the decimal 25? So I'll just write it up here. I don't have a blank page, but we have 25. We said we're going to take the 25 and we're going to divide it by 2. 25 divided by 2 is 12. 12 plus 12 is 24 with a remainder of 1. 12 divided by 2 is 6 with a remainder of 0. 6 divided by 2 is 3 with a remainder of 0. 3 divided by 2 is 1 with a remainder of 1. And 1 divided by 2 is 0 with a remainder of 1. So the binary number for 25 is 1, 1, 0, 0, 1. You can check your work if you're doing this for an exam. You can check your work by then going the other way around. So this would be 2 to the power of 0, right? Because this is digit 0, and so 2 to the power of 0 times 1 is just going to be 1, because 2 to the power of 0 is 1. So this equals 1. That's just in math, anything to the power of 0 is always going to be 1. 1 times 1 is 1. We don't calculate this one. We don't calculate this one. This is position 1, position 2. This is position 3. So this would be 2 to the power of 3. 2 times 2 is 4. 4 times 2 is 8. 8 times 1 is 8. This is 2 to the power of 4. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So then we add these three numbers together and hopefully we'll come out to 25. So we have 16 plus 4 is 20. 24 plus 1 is 25. So that adds up to 25. And then we have checked our work. And it means that, that's correct. And it means that my work is correct over here. So when you're calculating, when you're converting from binary to decimal and decimal to binary, you can check your work that way. So here we're adding two binary numbers. It's super easy to add the binary numbers. We're going to start with the least significant digit, which is on the right hand side, which is just wonderful because that's how we add numbers, right? Anytime we add numbers, we always start on the right hand side. We never add from here to here. We always add from right to left. So 0 plus 1 is 1. 0 plus 1 is 1. Now here we have 1 plus 1. We can't write a 2 here. So we're going to write 0 and carry a 1. And this will be 1, 0, 0, 0, 0. So whenever you have 2, you're going to write 0 and carry a 1. And that's for addition. So it's pretty simple. Okay, integer storage sizes. So this is our standard sizes for integers. 1 byte is 8 bits. A word is 2 bytes, which is 16 bits. A double word is double one word, so it'll be 32, and a quad word would be 64 bits. So 8 bits, 16 bits, 32, 64. And we always know that 1 byte equals 8 bits. So here we're going to look at the ranges of unsigned integers, and I don't know if I went over this, but unsigned integers are going to be always positive. Signed integers which we'll talk more about also in a minute, signed integers are going to can be positive or negative. So this is the range of unsigned byte. Unsigned byte is 0 to 255. That is how much it can hold. So it can hold the decimal numbers from 0 to 255, and that's what we can hold in 1 byte. In 16 bits, we can hold this range. Double word, we can hold this range, and unsigned quad words, we can hold this range. So that's how big your integer can be. So if you're thinking about, for example, if you're coding in C, and C++ or Java, and you have an integer, right? You're getting data from the user, and you're like, okay, I got to get somebody's age, and well, the age, nobody is more than probably 110. That's probably going to be like the maxed age. And so you're like, well, what am I going to use, the byte, a word? Well, if it's an age, I mean, there's no reason to use up this much memory. And right now, we don't have, at this time and age, we don't have to worry as programmers. We don't have to worry about managing memory. When I started programming, I worked for a company called Tandy, and I was a software programmer for that company. I worked on programming point of sale systems, not operating systems, point of sale systems. And we actually did have to think about, okay, do I need 2 bytes, or do I need 1 byte, or do I need 4 bytes? We really had to make sure that we didn't use a ton of memory, because we didn't have a lot of memory like we do now, on our systems. So it's important that you know what a byte can hold. And so if you have an integer that's a 4 byte integer versus a 2 byte integer, then which is short integer and long integer, then you can decide like which one to use depending on what data you're needing to get. So that's why it's important to know how big a data size is, and what's the range of the decimal that it can hold. Okay, so now we're going to talk about hexadecimals. And if you've taken a C++ class, hopefully you've taken a look at, or C class, you've taken a look at what's when you create a variable. If I can gather my thoughts, when you create a variable, it assigns a memory location. That memory location, the location itself, is a hexadecimal number. You can view it by hexadecimal number. So memory locations are represented in hexadecimal numbers. So it's good to understand what a hexadecimal number is, and what it means. And then we're also going to look at how binary values are represented in hexadecimal and also in decimal format. So in this little chart here, we have binary numbers, how they're represented as a decimal number, and then what's the hexadecimal number for that. So with hexadecimal numbers, notice that 0 through 9 are going to be just like the decimal numbers. So decimal 0 is hexadecimal 0. Decimal 1 is hexadecimal 1, all the way to 9. Well, after 9, we then start representing this hexadecimal number as a letter. And we're going to go to 15. So we have A, B, C, D, E, and F. A, B, C, D, E, F. And so that's how we represent our decimal to hexadecimal. That's how it corresponds. That's pretty simple. We already talked about how to go from binary to decimal. So if you can go from binary to decimal, then it'll be easy to go to hexadecimal. You basically have to always go from, if you're binary, you always have to go to either decimal or hexadecimal, and use the way that I showed you how to calculate to go to decimal. So let's look at these binary numbers here. So each hexadecimal digit corresponds to 4 binary bits. So each hexadecimal digit corresponds to 4 binary bits. So here we're translating this big number right here, and we're going to translate it to hexadecimal. And then if you want it, you could translate it to decimal from here. So first, we translate 0, 1, 0, 0. So if you remember, we don't care about the zeros, right? We only care about the 1. The 1 is in the third spot. The second. 0, 1, 2. So it's 2 squared. So 2 squared is 4. And then here we have 2 to the power of 0 plus 0, 1, 2, 3, 2 to the power of 3. So we have 8 plus 1 is 9. Okay, for this one, it comes out to 10. And when it comes out to 10, we have to not put the number 10, but we're going to put the letter A. So here is 0. This is 2, 4, 2 to the power of 0, 2 to the power of 1, and so this comes out to 1, and this comes out to, no, that comes out to 2, that's right. So it comes out to 2, and it comes out to 8. And 8 plus 2 is 10. And then this one is 6, and this one is 1. So for every 4 binary bits, you have 1 hexadecimal number. And hex means 16. So this is 0, 1. Yeah. Okay. Okay, the next thing we're going to look at is converting hexadecimal numbers to decimals. So again, a hexadecimal number is a base 16 number, and it's the numbering system that we use for addresses. So when you look at an address in memory, so if you have a piece of data, right, so you have let's say an integer, a number, a whole number, and you save it in, you make a variable for that number. So that variable takes up space, that number takes up space, and the address is in a hex. You can see the address of where that is in memory, and it has a hexadecimal number. And we're going to look and see how we add hexadecimal numbers, and that comes into play when you need to, if you're at one memory location, you have to get to the next, the memory location right next to it. Then you can do this addition of addresses. So we're converting hexadecimal to decimal. And so what we're going to do is, just like when we did the binary, you're going to take, you're going to multiply this time by 16 to the power of wherever the digit sits. So for example, this would be position 0. This is position 1, position 2, position 3. So that is the exponents. So we're going to multiply whatever number. So if this is the hexadecimal number, we're going to multiply 1 times 16 to the power of 3, 2 times 16 squared, 3 times 16 to the power of 1, and 4 times 16 to the power of 0. So you'll do each one of these. So remember, 16 to the power of 0 is 1. So 1 times 4. So this will be 4 here. And then this will be 16 to the power of 1. So remember that this will just give you the number itself, 16. And then we have to multiply 16. So I'm getting out my calculator because I'm not going to do this in my head. I don't want to do it in my head. So it'd be 16 times 3, which would be 48. This one will be 16 times 16. And 16 times 16 is 256. And then we take that 256 and we multiply it times 2. So this is 512. So when it comes to your assignment, you're going to be doing this, and you're also going to be doing this on your tests. So you just need to know that hex is base 16. So you multiply each of your numbers times 16 to the power of the position of that number. And then 512 times 16. So 16 times 16 times 16 is equal to 8,192. And then we multiply that times 1. So it just stays at 8,192. And then you're going to add all those together. And I did something wrong. Let's see, 16 times 16 times 16. It's 3 16s. Oh, this is wrong. I don't know how I got that. This is 4,096. Okay. I multiplied it times 16 one too many times. And now I'm going to add the 512 to the 4,091, and I'm going to add the 48, and I'm going to add the 4, and it does come out to 4,660. Okay, so the next thing is that we're going to look at this one. This one has a B and an A. Remember that A is 10, so we're going to just go 1 through 9, and after 9, we can't use 10 because 10 has 2 digits. So this is 10A. And you know, if you play cards, you know that the ace is the ace 10, right? And the jack is 11, the king's 12, maybe. Okay. And then B is 11. Okay. So we're just going to say 3 times 16 to the power of 3. 11 times 16 squared. You can't see this back here, but it says 10 times 16 to the power of 1, and 4 times 6 to the power of 0. And if you calculate that, you can pause it, work it out, and this is what the total should be. Okay, so if you want to just pause the video for a minute, work each of these out, and then see if you get this total. Okay, so we're going to try this out. What I want you to do is to convert 1100 1011, so this binary number, to hexadecimal, and then convert this hexadecimal to decimal. Okay, so what I want you to do is pause the video, try it out, and then unpause it. Okay, so the first thing that we're going to do to convert a binary number to a hexadecimal number, if I can say it, is we're going to divide our binary number. So we're going to have 4 digits and 4 digits. And if you have like more than these 8 digits, like 16, then just divide 4, 4, 4. Then the next thing is we're going to calculate the decimal number for each one of these. So if you remember binary, the base is 2. Bi means 2, like bilateral, binomial is 2. So the first thing that we're going to do is, so remember this is position 0, 1, 2, 3. So this would be, I showed you the answer over here. That's okay. Okay, so first this will be 2 to the power of 3. And then this will be 2 to the power of 2. And 2 to the power of, this is 1, sorry. 2 to the power of 1. 2 to the power of 0. And we're going to skip 2 to the power of 2. So this would be 1. So this one equals 1. 1 times 1 is 1. This one equals 2. 2 times 1 is 2. And this one is 2 times 2 is 4. 4 times 2 is 8. So soon you'll just remember is 1, 2, 4, 8. 8 times 2 is 16. So 8, 16, 32, etc. Quickly you'll just start to remember that the 0 position is always 1, position 2 is always 2, position 3 is always 4, 2 is always 4, 3 is always 8. I messed that up. So I already know what these are. So this one's just going to be 8, and this one's going to be 4. I just know that by heart because I know that 2 to the second power is 2 squared is 4, and 2 cubed is 8. So 8 plus 2 is 10, plus 1 is 11. 8 plus 4 is 12. And then remember in hexadecimal, 11 is B, because 10 is A, and 12 is C. So the hexadecimal number for this binary number is CB. All right, so here we're converting F210 to decimal number. And so we'll take the first digit, which is F. F is 15, because remember we go from 9, A, B, C, D, E. See my hand? There it is. F. So A, B, C, D, E, F. So that is 15. Or let me do that again. 10, 11, 12, 13, 14, 15. So 15 times 16 to the third power, because this is the third position. 2 times, this is the 2. This is F. 2 times 16 to the second power, second position. This is the first position. Oops. So 1 times 16 to the first power. And then this is just 0 times 16 to the 0 power. Anytime you have a 0, you don't have to even calculate it because you know that 0 times anything is going to be 0. And then you're going to calculate these right here. So this will be 16 times 1. 16 to the first power, 16. 16 squared, you said was 252 earlier. 16 times 16, sorry, 256. And then we multiply that times 2, and that's 512. And then we multiply 16 times 16 times 16 equals 4,096. And 4,096, we multiply it times 15. And this equals a big number, 61,440. And then you add all these up and it gives you the decimal value. So let me add those up. So hopefully I did my math correctly and I added them all up. I don't have the answer, but that should be it if I did my math correctly. Okay. Powers of 16, used when calculating hexadecimal values up to 8 digits long. So basically, this is just showing you a table of the values of what is 16 to the 0th power, what is 16 to the 1st power. I guess eventually, if you have to do enough of these, you would memorize them, but you can just use a calculator. Okay. Converting decimals to hexadecimals, just like we did the others, you're dividing by the base. So you take your decimal number, whatever, decimal number are our numbers, decimal system, and then you divide that by 16, and the remainder is going to be your hexadecimal number. So here you have 422 divided by 16. So when you divide that using your calculator, you'll see that you have a remainder of 6. And if you're using the calculator to do this, I guess that just a regular simple calculator, the easiest way would be you would do 422 divided by 16, and then you take that you take the whole number that gave me 26. So I'm going to take that 26 and I'm going to multiply it by 16 and subtract it from 422, and that will give me the remainder of 6. This one's a little bit easier to do in our head, right? We know that 16 can only go evenly into 26 one time, and the remainder is going to be 10, right? Because 1 times 16 is 16, 26 minus 16 is 10. So here's 10 right here. And then this one will be 16 goes into 1 0 times. It does not go into 1, with 1 remaining, 1 as a remainder. So our the number 422 in decimal form is the same thing as 1A6 in hexadecimal. Okay, in this slide, we're going to look at how to add hexadecimal numbers. So remember that we want to do this for memory, when we're looking at memory for that purpose. So you're going to divide the sum of 2 digits by the number base, 16. The quotient becomes the carry value, and the remainder is the sum digit. Okay, so what does that mean? So let's take a look at this one here. So we have B plus A. So remember, A is 10. B is 11. Okay. So 10 plus 11 is 21. So here's 21 right here, 21. They've taken the 21, divided it by 16, sorry. So 16 goes into 21 one time evenly. Plus that 1. 1 times 16 is 16 with a remainder of 5. So 16 plus 5 equals 21. So you take this number, divide it by the base, and the remainder is going to be your least significant digit. And then this 1 right here is going to be our carry. So there's the 1. So now we're going to add 6 plus 4, which is 10, plus 1 is 11. 11 is B. We don't have to do anything special. If your answer when you add these, if it's 0 through F through 15, then if it's a 15, 14, 13, 12, 11, 10, 9, 8, so on, you don't have to do this here. This is only if it's greater than 15. So 8 plus 8 is 16. So for 16, we know that it's going to be 0 and we carry 1. Well, how do we know that? Well, 16 divided by 16 equals 0. With a, I'm sorry, 16 by 16 is not 0. 16 by 16 is 1 with a remainder of 0. So this is the remainder. 1 is the carry. 5, 6, 7, 8. 8, 9, 10, 11, 12, 13. D is 13. 4, 5, 6. 6, 8. 4, 5, 6, 7. Boom. That's addition with hexadecimal numbers. Okay? And here at the bottom, it just tells you that it's an important skill. Programmers frequently add and subtract the hexadecimal addresses of variables and instructions. Hexadecimal subtraction. When a borrow is required from the digit to the left, add 16 decimal to the current digit's value. So when you have to borrow, you know how when we borrow, when we're adding decimals, we borrow 10. Well, here we're going to add 16 instead of 10 when we borrow. So here we want to subtract 7 from 5, but we can subtract 7 from, okay, so we're going to do it just like we subtract in regular problems. So I can't take 7 away from 5, so I'm going to borrow 1 from the 7, and when I borrow 1, I'm not going to add 10, I'm adding 16. So 16 plus 5 is 21, so this here becomes 21. Okay, so I borrowed 1 from the 7. When I borrow 1 from the 7, I'm going to add 16 to the 5. So 21 minus 7 is 14, and the letter E represents 14. This is 14. That's what the E represents. Remember, A is 10, and then count from there. A, B, C, D, E. Here's my hand. A, B, C, D, E. 10, 11, 12, 13, 14. Okay, so now I took 1 away from the 7, so I no longer have 7. I have 6. Oops, there's a 6. 6 minus 4 is 2. 6 minus 2 is 4. C minus A is 2. Remember, this is 10. B is 11. C is 12. 12 minus 10 is 2. So that's how we do subtraction. So subtract just like you would normally have done in elementary school, except you're going to, when you borrow, you add 16 instead of 10. All right. Okay, let's see if I can. Okay, no. Let's see how to get rid of my pencil. Okay, so we're going to practice subtracting hexadecimal numbers. So here would be a useful reason to do this. Remember, hexadecimal numbers are the addresses of our variable. So if we have a variable that is at this address, and then the address of the next variable is here at this address, how many bytes are used by variable 1? So what we want to do is we want to subtract this from here. That gives us the hexadecimal value of how many bytes are used by var1, and then we're going to convert that to decimal and we'll know the total number of bytes. So this is an address, kind of like you have a street address and you've got a house at 100 Main Street and the next house is 102 Main Street. So if the houses were so it's just the address. Like if one is at 101, one's at 102, is like they're just like next to each other. So whatever comes next, it's at that address because this one took so much memory, took all that memory, whatever's between these two. So this is what, if you want to pause it and subtract this from here, so you would put this number at the top and you would put this number at the bottom and subtract it. So the difference between these two addresses will give you the number of bytes used by var1. Here's how you calculate the difference. So this will be the top number, this will be the bottom number. So a minus 0 is just a, 6 minus 2 is 4, and then the rest are just going to be zeros, because 0 minus 0 minus 0, 4 minus 4 is 0. So this is the hexadecimal number. Now you want to convert 4a to decimal. And when you convert 4a to decimal, you get 74. And remember to convert, if you're going to convert 4a to decimal, you would, this is position 0. So, position 0, and this is position 1. And your base is 16. So if you take this very first one, it would be 1 times a, which is 10, and this would be 2 times 4, 16 squared, 16 to the power of 1, which would be 16, and then, okay, let me just do this with a pen, because you're probably wondering, what is she doing? Okay, so this would be a times 16 to the power of 0, so it's 1 times a. 16 to the power of 0 is 1. 1 times a is just a, which is 10, because a is 10. And then this would be 16 to the power of 1, and that's times 4. Okay, so 16 to the power of 1 is just 16. 16 times 4 equals 64, and then so this here equals 64. 64 plus 10 is 74. So var1 uses 74 bytes of memory. That's a lot of bytes. 74 bytes is a lot of bytes. So I don't know what this is holding, but it's holding something really big. Okay. All right. If you don't remember how to subtract, go back and practice on subtracting the hexadecimal numbers. Okay, the next thing that we're going to look at is signed integers. So if the integer is unsigned, then it's just going to be positive. But if it's signed, it can be positive or negative. And the way that you're going to know that is by looking at the highest bit. So the highest bit of your binary number is going to tell you if it's positive or negative. Now, first of all, you're going to know if this is signed integer. You'll be told this is a signed integer. So if this is a signed integer, then look at the highest bit. If it's a 1, it's negative. If it's a 0, it's positive. If the highest digit of a hexadecimal integer is greater than 7, then it's going to be negative. So, for example, 8a would be a negative number, C5 would be negative, A2 would be negative, 9d would be negative. There we go. Okay, so this section can be a little tricky. This is on page 16 and 17 of your book. So the 2's complement is useful to processors because it's going to remove the need for separate digital circuits to handle both addition and subtraction. So this is at the top of page 17. So instead of having to have separate digital circuits to handle addition and subtraction, what the 2's complement does is allows us to take something like if we had a minus b, we can just say, well, that's the same thing as saying a plus negative b. So let me write down here. So a minus b is the same as saying a plus negative b, right? This is the same thing. So the processor, it takes this and it converts it to this expression. So the 2's complement of a binary integer, so when you have a binary integer, is formatted by inverting or complementing its bits by adding 1. So for example, if we have this binary number, we would reverse the bits, so all the zeros become 1, all the 1s become 0, and then we would just add 1 to the very last digit here. And this would then be the 2's complement representation. So this number would be the 2's complement of this value. So that's our additive inverse. Okay, so here we're looking at binary subtraction. So when subtracting a minus b, convert b to its 2's complement, and then add a to negative b. All right, so so let's say that we have this right here, 0, 0, 1, 1, 0, 0, minus this number. So this is a, and this is b right here. So the first thing that we're going to do is we're going to take b right here, and reverse the bits for b. So we would have 0, 0, 0, 0, 0. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we convert all these zeros to 1, These two are converted to 0, but remember you have to add 1 to the end here. So we would add 1 right there. So this right here would be the 2's complement representation of B is this. So again, I made all these 1s. I made these 2 zeros and I added 1 to the end. So this is the 2's complement for B. So I have to do that first. So now the next thing I'm going to do is I'm going to add. So I'm going to say 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 1 is 0. Here, I'll do it right here. This is 1. This is 0. This would be 0, carry 1. This would be 0 plus the 1, carry 1. 0. So 1 plus 1, and then we carry 1. 0, carry 1. 0, carry 1, 0. So if this is A and this is B and you have to subtract them, then this is going to be the answer of A minus B. So here's a practice problem. Try subtracting 0, 1, 0, 1 from 1, 0, 0, 1. So the way you're gonna set it up is by saying 1, 0, 0, 1, and you subtract this from that. So minus 0, 1, 0, 1. So practice subtracting those two. Okay. Learn how to do the following. So form the 2's complement of a hexadecimal integer. Convert signed binary to decimal. Convert signed decimal to binary. Convert signed decimal to hexadecimal, and convert signed hexadecimal to decimal. So here we're converting, but these are going to be signed numbers, or signed like binary numbers or decimal or etc. So that starts with converting signed binary to decimal. That starts on page 17, and it shows how to do each one of those. So here we're looking at the ranges of signed integers. So the highest bit is reserved for the sign. This limits the range, so this decreases the range. So the range of a signed byte is negative 128 to 127. And if you remember, let's see, go back in your book and give you the range, compare it to the unsigned. Somewhere here I give you the range. Nope, don't have it anywhere. Okay, so this is the range of assigned word, and remember that this is, so a byte, this is going to be 16. This is on page 13, a word is 16 bytes. So this is 8 bytes, this is 16 bytes. This is how much 16 bytes can hold of a signed integer. This is double the word, so this would be 32. This is what 32 bytes can hold of a signed integer. And then quad is 64 bytes, and this is how much it can hold. So basically we're saying that if you have a number that is between, like, you're going to get data, and the data cannot be greater than 32,767 and negative 32,768. That's going to be the boundaries of the integer. So again, this is 8 bytes, 16, 32, 64. And I really thought that somewhere on here it gave us the range of unsigned, but I can't find it. Okay, next. So if computers store only binary data, right? And we know that we can change a binary number to a decimal number. How does it store characters? So if it needs to store the letter B or the letter or the question mark. So the way that it does that is by using codes that map to the characters. And there's different types of character sets. This is one character set called the ASCII table. And so if we look at this ASCII table and we look for the capital A, here's capital A right here. So capital A there it is, in decimal format is 65. So the capital A is mapped to the decimal 65, then we can take that 65 and convert it to binary. And so that's how characters are stored as binary. Also, this is how we can compare characters. So let's say that we're sorting data and we want to sort last names. So we're sorting strings, we're sorting by last name. We know that A comes before B, and the reason we know that is because A is 65 and B is 66. So A, 65, comes before 66. And that's how we sort characters, things that have characters. That's how we can compare. We can say, is apple less than bear? And yes, apple A is less than bear with B. So we're looking at that first character, and then we look at, just like when we're sorting, if both starts with an A, then we look at the second character to see which one comes first. So here, these are different types of character sets. So we have the standard ASCII that has characters from 0 to 127. But then we have this one here, the Unicode. And the Unicode is used because most computers have to be able to represent a wide variety of international languages. So Unicode standard was created as a universal way of defining characters and symbols. So if you go to the internet and just do a search on the Unicode character set or the ANSI character set or the extended ASCII character set, then you'll be able to see what those are. In the back of your book, in the back cover, at the end of your book, you have the ASCII codes used when running in Windows console mode. So those are going to be the ones that we would use. So if you're like programming in C++ or Java, then we usually refer to the ASCII character set. Null terminated string. So if you know you've had a programming class before, of course, to take this class, so you know what an array of characters is. An array of characters is a string, like if you have the name Apple, APPLE, that's an array of characters or character string. And at the end of that character string, you're going to have a null byte. So it is null terminated, and that the null byte is a 0. That's the 0 in the ASCII character set. Okay, if you look at the ASCII table, you're going to be able to see, so we looked at earlier the ASCII table, and we saw that capital A had a decimal digit assigned to it that was 65. So a binary integer is an integer stored in memory in its raw format, ready to be used in a calculation. Binary integers are stored in multiples of 8 bits. So 8 bits equals 1 byte, 16 bits equals 2 bytes, so on and so forth. An ASCII digit string is a string of ASCII characters such as 1, 2, 3, or 65. This is simply a representation of the number and can be in any of the formats shown for the decimal number 65. So 65 in binary digit string is this. This is how it's represented. This is the decimal format. This is the hexadecimal digit string. And this is the octal digit string, which we have not talked about. And we're not going to cover this one. So this is just how it would be represented. And if you look at the ASCII table, it shows all these different formats for 65. Okay, the next section is going to cover Boolean operations, and I'm going to go ahead and make a different video for that since this has already gone pretty long. And that one is a pretty short section on Boolean operations. And it should be a review from other classes. It's just going to show you how we represent or how we show Boolean in assembly language, okay? And then just show just review on the different, looking at the truth tables. Yeah, so we'll go through that one in the next video. Okay, thank you.